it is denoted by, there are some symbols for denoting cardinality, O of A, order of A, okay, which is nothing but the number of elements. Sometimes it's written like this also, or sometimes even using a hash symbol. All of them mean the same thing, that is the number of elements in A. Okay, so to understand this, however, we will be using mainly this. So to understand this more clearly, we consider these examples and write their cardinality. Cardinality of the empty set is 0. There is no element, so the number of elements is 0. Cardinality of this singleton set as well as cardinality of this singleton set, or I can write 0 here. They are equal to 1. Each one of them has only one element. Note that the sets are not equal. This set has 0, however, this set is nothing but the singleton set consisting of the element 1. So they are not equal, but their cardinalities are same, and that is equal to 1. So although this is the case, but we have this. Don't forget the brackets, otherwise it will mean something else entirely. Okay. And cardinality of this is equal to 100. So it's just the number of elements. Okay, now the next thing is, okay, do you remember the beginning of our video? After writing down the definition of a set as a well-defined collection of distinct objects, we emphasized the word objects, and we said that sets themselves are also considered as objects. So objects are things which can be anything, and they can be elements of a set. So because sets are considered as objects, they can be elements in some other set. So let us take an example of one such set. You take D equal to 1, 2, look at this set. Okay, D consists of 1, 2, and 3, 4. So you see that the set 3, 4 is itself an element of D. Okay, so this set can be an element of another set. This may sound strange or complicated at first, but you will soon be accustomed to this, and in fact this concept arises quite often in mathematics. Sometimes even this can also be an element of another set. So that type of complexity will arise in the higher parts of mathematics, and in fact you will see that they are not just something to be considered for the sake of it. They become a necessity. Okay, now let us see some things about this set D, since it has one of its elements itself as a set. So you consider these statements. One belongs to D. Okay, one belongs to, this is a true statement. One definitely belongs to D. What about this statement? 3 belongs to D. Is it true or false? Actually, it's a false statement. But why? You see, when we use this symbol, we mean that whatever lies on the left hand side is inside the set on the right hand side as an element. Do we see 3 as an element here? Actually, we can see 3 here, but 3 is not an element of D. Why? Because D has 3 elements, 1, 2 and this set. So although 3 seems to be inside D, but 3 is not an element of D. So 3 does not belong to D. Okay, so these things should be kept in mind, and they can create a lot of confusions. Now we come to the relation of being a subset of a set. Can I write 1 is a subset of D? No, of course not. This does not make sense. Whenever this symbol is there, both the sides should be sets. The right hand side is a set, the left hand side is not a set, it's just a number. However, if I write this singleton set, then this is a subset of D. Why? Because every element in this set is also an element of D. This set has only one element, which is 1, and that is definitely in D. So this is a subset of D. Now if you think about this, is this true? This, however, is not true. But you may say that both the sides are set. Of course, both the sides are set, but you have to see whether the condition of being a subset is true or not. Every element in this set must be in this set. 3 is an element in this set. Do you have 3 here as an element? No. Similarly, 4 is also not an element of D. That's why this is not a subset of D. However, if you consider this statement, first make sense of this symbol. What does this mean? This is a singleton set whose only element is this. Okay, so it's again a set whose element is a set. Now for this to be a subset of D, every element in this set must be in D. It has only one element, and that element is 3, 4. Whether 3, 4 belongs to D? Yes. 3, 4 belongs to D as an element. So that's why this is a subset of D. So do you see how complicated things can become when one of the elements or several of the elements of a set are themselves sets? You have to keep track of the level. Okay, so you can think of these things as primitive elements, and then sets consisting of primitive elements as sets, that is one level up, and then set whose elements can be primitive elements or sets, one level up more. Okay, so if you can keep track of whatever happens, however complicated the situation may seem, all you have to do is go back to the definition and see what the statement is meaning. You have subset, relation, you have to go back to the definition of subset and see what that definition says. From that you can figure out what is happening. Okay. Now, because sets of sets have arisen now, so we come to a special type of sets of sets. Let A be any set then, okay, now A is any set. So let me simultaneously take an actual example. A is any set. Any set means here we have taken this particular set. The set of all subsets of A is called the power set of A. And is denoted by P of A, or this peculiar symbol 2 to the power A. Now, what does this? This is a new definition. Okay. So if a set A is given, then you consider all the subsets of A. Take that collection. That collection will be a set. That set is called the power set of the original set A, and it is denoted by P of A, or 2 to the power A. That is, P of A is equal to the set of all objects B such that B is a subset of A. Okay, it seems somewhat complicated at first, but let us work out the power set in this particular example. So that means, oh, I forgot to tell you one more thing. Let me say it here. You consider any set, okay, let A be any set. What do you think of this relationship? The empty set is a subset of A. You see, go back to the definition of subsets. This means X belongs to the empty set implies X belongs to A. This is the meaning of being a subset of another set. Now again, this is an implication. So to see whether this is true, you have to check that if either the hypothesis is true and the conclusion is true, or the hypothesis is false. In this case, the hypothesis is false. Okay, empty set is empty, so there can be no element in it. So this statement, this implication is vacuously true. True nonetheless. So that means the empty set is indeed a subset of A. So the empty set is a subset of every set. Okay. And why I am saying this now? It's because we are going to write down all the subsets of A. So first of all, we have empty set. So we write that down. Then what can be other subsets? You see, if you try to actually find out subsets of a given set, this definition may seem somewhat difficult. Instead, what you think of the situation is like this. This is a given set. You try to find smaller sets inside of that set. So, are these subsets? One, of course, yes, the only element 1 in this set is again here. So in the same vein, 2, 3, these are subsets. But there are more. In fact, let me clean this part so that I can write all the subsets. So these are singleton subsets. What about subsets having 2 elements? There are 3 such subsets, 1, 2, 2, 3 and 1, 3. But there is one more, the set itself. Every set is a subset of itself in a trivial manner, because if x belongs to A, then of course x belongs to A. This becomes a trivially true statement. So A itself also comes as an element. So this is the power set of A, this particular A. So that is the meaning of power set. Now, from this example itself, we make 2 observations. Observations. Number 1. P of A seems to be larger than you see here A has only 3 elements, but P of A has many elements, many more elements. So P of A seems to be larger than this. Okay, but before making these observations, let us try out the power set for some smaller sets, so that we don't have to rely on only one example. What about the power set of the smallest set possible, empty set? You have to find out the subsets of the empty set. Clearly, because empty set will always